So the plan for this lecture, and I'm assuming next lecture too, I don't think I'll be able to finish. I didn't have finished now all the way, but now that we talked a little bit about the Riemann surfaces, I wanted to take a step back and actually look at the angle, which is the solution of the Kdv equation, and that's solved through the Riemann surfaces. And in this talk or this meeting, I want to focus on a specific example, and the example of a genus 1 surface, and in particular the Kdv equation. We can actually do it for genus greater than 1 for any genus. It's going to create a family of solutions, and also we can do Kdv equation, which also includes an extra variable, y variable. But in this case, I wanted to just give out the solution for the genus 1 case, where all the formulas and all the concepts simplify, but and kind of just grasp that, and then generalize later to other genus. Because I think once we have a better understanding of genus 1, it's easier to move up to higher genus. So that's my focus for today. Just focus on a specific example of genus 1, and so the differential, and then. But let me, before I move on, so today I'm just gonna give you the solution, and even defining the solution, it involves different objects and definitions from the Riemann surface, and so I'm gonna spend most of the talk just talking about defining different objects that we need for the solution, and then the aim is for the next week is to actually show that it's indeed a solution. So here I'm just defining a solution, and next week I'll show that it is a solution, and then after that we can move on to higher genus. So let me start with the Kdv equation. It's this nonlinear partial differential equation. Solving nonlinear partial differential equations are hard. So this is the whole goal, that we're trying to find different solutions for this nonlinear partial differential equation. So in here, what we're doing here is that from the Riemann surfaces, we're going to give different solutions, or a family of solutions. And in here, I'm working with a specific solution, which is written this way. And again, the purpose of this talk is to clearly define everything that's going on here, or like maybe not as clear as possible, but a very good idea. In here, we have the double derivative, partial derivative with respect of x of log of this theta function. The theta function, it can be defined as this e to this sum, where you're taking a sum over the integers, and you have b, some constant, which has negative real part, and then you take this sum. The fact that it has negative real part makes this this sum converge. It makes this well defined. And for higher genus, in all that we're doing right now, b is going to be just a scalar. But for higher genus, this b is going to become a matrix, G by G matrix. But right now, I want to simplify everything, and it's just going to be a 1 by 1 matrix, a scalar. So we're going to have this, and then we're going to have this other scalar, this other parameters, u, w, d, and b, which in this case, they're all going to be scalars, and they're going to be determined by the Riemann surface, by the torus. And in particular, I'm considering this case of this hyperelliptic function equation, where we've defined, we've seen how it's a covering. We've seen it's a covering of the plane, and we've defined this Riemann surface this way. But yeah, so this is the goal. We're going to try to define this. So my goal for today is this constants, which for higher genus, these constants are going to generalize to I want to say either vectors or matrices. I forget at this point, but they are higher dimensional objects. Let me start with defining more objects on the Riemann surface. So the first thing that I want to talk about is cycles. Ooh, a little bit chilly. Cycles. So I'm going to introduce this idea of cycles or sheets of the Riemann surface. So in here, this copy of the complex plane is the base of this degree 2 covering of this Riemann surface, and I'm going to pick a point x naught in x naught y naught in the base, or wait, in the Riemann surface. The Riemann surface is defined by this. I'm going to pick a point there, and I'm going to parametrize a curve that travels around the base, where, for instance, in this case, it's just going to be a counterclockwise circle that's close to the origin for 0 and 2 pi. And I'm going to analytically continue I'm going to lift this path up to the Riemann surface, and starting with the point x naught, y naught. And what I really mean by analytically continue is that I'm going to look for solutions of this equation, such that, so if I look at solutions of this, I have either a plus or minus square root, and I'm going to choose the plus or minus consistently so that y of x is continuous. And in here we have that y of x naught has to equal to y naught. So this is going to fix our point in when we lift this curve. The first point is going to so it's going to fix it as y of x naught, and then this is going to fix a sign, either plus or minus. And then when we keep moving this way, we're going to make the sign consistent. And in particular, we can do this fairly explicitly if we take x naught to be small. And in here, I'm also taking G3 to be 0, just for making everything simple. So if we have that, then if we have x naught to be small, then, and we're parametrizing the curve, we're parametrizing the curve C. This is going to be epsilon e to the I theta. So it's going to be a small circle going around the origin. And we're trying to look at for solutions of this equation. So we're looking for solutions of this. And in here, oh no, sorry. We're not looking at solutions. This quantity for this x is going to be roughly, since this is 0, we take this to be 0, this is going to be epsilon cubed. It's just going to be roughly negative G2 epsilon EI theta. So when we solve for this, this is just going to be the square root of this quantity. And in particular, we're going to have, and then the angle is divided by 2, and we see that y0 is going to be this quantity, and then after we travel 2 pi at full circle, we're going to come to the other side, but we're going to arrive at a different sign. So in here we see that we're not arriving at the same point, and this is because we're going through this, we're going through a cycle that encloses one of the branching points that we discussed last time. So whenever we have cycles, and we do an analytic continuation and we go around them, if there's a branching point inside of them, then we may not come back to the same position. So for this, I want to motivate this idea of cycles for the Riemann surface. And in here, I'm going to have this H1 X with complex coefficients is the space of simple closed curves in X, such next the Riemann surface, such that gamma 1 and gamma 2 may be continuously deformed. And what we're doing here for the torus, we have that gamma, this is going to be gamma A, and this is going to be gamma B. And when you project from the double covering, you have that the image is going to be this cycle for a specific choice that is going to enclose two of the branching points, and this other cycle that's going to go, that is also going to enclose two of the branching points. And we saw that from the previous computation, we see that we cannot deform this cycle any smaller to just include one point because it doesn't connect back up. It breaks up into something that's not discontinuous. So the smallest cycles that we can keep before they break up into a plus or minus are the cycles that include two branching points. And you can see that this are going to be, for this Riemann surface, we're going to have this two cycles. These are going to be two cycles, and we have then the space that of cycles that may be continuously formed that are equivalent up to continuous deformations is going to be this space H1. And for Riemann surfaces, this H1, the space of cycles, is going to be vector space of dimension 2G, and it's a linear space. And for G equals 1, which is in this case that we're working with, we're going to have we're going to have a two-dimensional space, and the bases that we choose are going to be these two bases, this and this, which in the torus may be thought as this two cycles. And that means that for any cycle up to, we can write any cycle up to continuous deformation as a linear combination of these two cycles, A and B. And for some pair of integers. So this is one of the basic objects here for this Riemann surface, and for genus greater than 1, you can generalize this idea of the cycles, and you'll have 2G linearly independent cycles. Let me know if you have any questions at any point. Yeah.
You use a Z at the very end is absolutely correct. So at the top, when we say H1 that's C, that's really Z instead of C. And then what's going on is you can tensor that and turn it into the vector space. Yeah, that one's really the Z.
This one.
Yeah. And that's why down at the bottom it's spot on right with a Z for G equals 1. And what happens is some sort of way, it's like, oh, you know, it's going to all work better if we use complex numbers.
Yeah.
Right.
Yeah. Yeah, because if you're using complex numbers, then you're working with vector spaces and you're not doing rings, and like all the torsion stuff falls out.
Exactly.
So
errors of read, if you like this, the first thing actually is reviewing group. But later you're going to want to do stuff with complex numbers.
Yeah. Yeah, because in particular for complex numbers, you have stronger tools of linear algebra. Yeah, thanks for that comment. So yeah. So now I'm want to briefly talk about functions and one forms and the Riemann surface. Because again, the solution that we're going to come up with the Kdv equation, it depends on functions that we're going to define on the Riemann surface, and additionally, we're going to define differentials on the Riemann surface. And I just want to make sure we're on the same page on this. So here, when I think of a function that maps from my Riemann surface to the complex numbers, what I really think is a collection of functions on the different charts or different small subsets of my Riemann surface that have a certain compatibility condition. And so for my Riemann surface, the way that, as a manifold, the way that it's defined, and we have a collection of charts, which is really small open subsets of the Riemann surface that have homomorphic mappings or mappings to small subsets in the complex plane. And so that these mappings are compatible, meaning that if you come back up and go back down and you obtain this map, we have this phi2 composed with phi1 inverse, that these maps are homomorphic. And this is how we build our manifold by this local coordinates, which again, the local coordinates is this object, this map between u tilde and u1 and phi1, such that they're compatible homomorphically. Then what I think about then when I'm thinking about a function, instead of really thinking about the function in the Riemann surface, I really think of it in the local representation down at the base after the map phi. So what I introduce here is a local representation, and here you can actually write it as a complex function, where in here this is a subset of the complex plane. So you can really use the tools of complex analysis as we know them and apply them for the local representation. So these are just going to be complex functions, holomorphic complex functions. And we're going to have a collection of these fi functions that are defined on each of the local coordinates, each of the local charts. And they have to satisfy this collection of functions. They actually have to satisfy a consistency condition so that it's a well-defined function, so that if we move from one coordinate to the other, they actually give us the same value when we evaluate it. And the consistency condition, it's fairly naive. It really means that if I evaluate something here and then I bring it back here via phi1, and then I bring it down here via phi2, then I should obtain the same value. So in the u1 and u2 case, if I have my function f, which is defined on the whole Riemann sphere or Riemann surface, I have it for a local chart defined at u2. So it's a map that takes me from a local an open subset of x to the complex. And then by using this chart, this map into the complex plane, I can define this function that I call f sub 2, which is f composed with phi2. And then if I want to consider the same function and make sure that it has the same value, then what I do is I have this transition map phi2 and then I just follow the function this way. And in here, we can be more explicit and see that this is fairly easy to check. Fi is really f of phi I, and phi ij is phi I. this should be inverse, and this is Vj. There we go. F inverse. So this is my F of Vj inverse, so Fj. So it's going to be a collection of functions that have this consistency condition. And this is the way that I really think of functions in my Riemann surface. And in particular, we can just think of functions going from complex to complex that satisfy certain consistency conditions. So, and in particular, I want to go through this, and moreover, in here, if I say that a function is f is holomorphic, if each of the fi's is holomorphic. So I can check the holomorphic condition by checking at local charts, at each individual local chart. So this is the way that I'm thinking about functions. And one of the particular reasons why I wanted to go through that is because I want to contrast that with the definition or the way that I think about differentials on the Riemann surface, because what we're going to do is we're going to want to define integrals on the Riemann surface along the cycles. And here for the differentials, it's a similar story where I'm going to think of differentials as defined local charts, and then by defining a local chart, I can map to the complex plane, and then think of it as just as a complex differential. So, and then use the tools from complex analysis. And I can write everything as an expansion of a complex differential. So in here, this might be a little bit technical, but I just want to make sure that we're on the same page. In here, a differential is going to be a map from X to this cotangent space section, really. This is dimension 1, and this is dimension 2. And in particular, if I look at a small subset of X as at a chart, then we have this inclusion map. So I have this map here, and then I can restrict the differential. And this cotangent space is going to be T1. It's going to map into a cotangent space of UI tilde. And then I introduce my local chart, my local coordinate, which is going to be my phi, which is going to map from a small subset of X to a small subset of the complex plane. And then this map is also going to come down, and we're going to have a map from UI and the cotangent space of UI. And here we have a particularly nice representation of the cotangent space. It's actually a product space of UI and the complex numbers. So what you would say is that the cotangent space trivializes. It becomes a product space, because in general, over here at the top, it's not generally a product space. So, but in here, we can separate the coordinates out. And in particular, now what this means that if we pull down this differential all the way to a local coordinate, it means that we have a map CI to a pair CI, which is just the identity on the UI coordinate, and then some other function WICI. And the notation that in the way that differentials are written, and that you'll see in the book, is that it's written as WICI DCI, the way that we write differentials in a typical calculus class. So again, the idea of how to think about differentials and how to work with them is to do them in local charts. And the same way that we had functions, the way that we work with functions on the Riemann surface by local charts, we had some consistency condition. And here for differentials, we're also going to have a consistency condition. and to transform from one coordinate to the other. And this is going to be a different consistency condition than the function. So it's going to be slightly different object. So in here, we're going to have CI is my local coordinate. And if I want to change my coordinate from CI to CJ, I apply this transition map. And then just by doing calculus, I have that DCI is phi prime ij cj dcj. This is the Jacobian. And this is my change of coordinates for the base space. And then this is going to be my change of coordinate formula for the cotangent space. So I'm going to have this be my transformation to change from one coordinate to the other. So when I have Wi dci, by introducing this change of coordinates, I have that Wi ci, I replace ci here with phi j cj, and dci, I replace it with this, and this is going to be my wjcj. And what this means is that my differentials, my functions here on my local functions for the differential are going to transform as following. With wj is going to be the product of wi composed with phi j times the Jacobian. So this is the typical consistency condition for the functions, but if we're in differentials, we have to introduce this additional term, which is the Jacobian, which is the interpretation is that it's it adjusts for the volume or the mass from changing from one coordinate system to the other. So this is going to be the way that I think of differentials. And in particular, this is really so that I could write differentials in complex coordinates, as if they were like elements in the complex, as a complex function or a typical differential in the complex plane. And again, if this differential is going to be holomorphic if each of the wi's in the local coordinates is holomorphic. And I think that's what I want to say, because yeah. So we want to work on them this way. Now I'm just double guessing myself whether I've written all the consistency conditions. I think there might be a consistency condition with the intersection of 3 maps, but in any case, they transform this way. So this is the way to think of differentials in a Riemann surface by its local coordinates. Question?
Yeah, no, I'll offer very quickly a complementary view. So you could have started with tangent vectors instead of cotangent vectors.
Mm-hmm.
And tangent vector you probably see physically, you have some picture of it. And now you can take a tangent field. You're used to thinking of that as well. So that x goes into t different one of x at the top. And now these differentials, there's something that can evaluate each one of those elements of the vector field.
So yeah, a vector field are like lines, and these are going to be defined at each point, and these are going to be t1 of x.
Yeah.
And that's going to define. So then the cotangent space is going to be the dual object to this. It acts on vector fields and it evaluates essentially the length of that vector. That's one interpretation. But for me, that's too abstract to work with.
It's an easy picture, but when you want to go down and really do nitty-gritty calculations, then the local coordinates.
Yeah, you can't get your hands dirty with these dual objects, or you could, I guess. Depends on how you get your hands dirty. But yeah, for this is for me, this is the working interpretation of the differentials. So now let me bring it back to our example. So in here, again, x is going to be defined by this polynomial equation, and it's going to be a torus, and it's going to be a double covering over the complex plane, which is down here. And then we have the branching points, which are going to be given by this, that map down to the complex plane E1, E2, E3, and infinity. The last branching point is going to be an infinity. I'm assuming that all these E's are real. And we're going to have, for this, in this case, we're going to have two charts or two functions. So for any point x, y here, we can define the projection map, which we simply call x, to just project x, y, a point to the base curve x. But again, at this point, as we discussed in the previous meeting, these points are ramification points and they're no longer homomorphic. So this is not going to be a chart. So we introduce this second chart where we project to the y-axis. So that's an additional chart. And these two charts should be enough to describe all the points in the Riemann surface by some open map. So a specific homomorphic differential is going to be given. So in here, this is going to be for a subset that I call U. U1 is going to be, it's not going to include the points, this points. It's going to exclude this points. Because then this chart is no longer homomorphic. So this is for U1. And then U2 is going to be some other open set of the Riemann surface that does include these points. But in any case, the differential that we're given and the book uses is going to be this dx over y. And if you write it in local coordinates for this chart for U1 for points away of the branching points, then you can substitute y by a specific solution of this. This is going to be either plus or minus, as long as you're consistent, and you're going to have this local representation. And here, we can really think of x as being a complex number that's not one of the EIs. And away from all those points, it's easy to check that this is going to be, this is homomorphic, since this is not going to vanish, since the square root doesn't vanish. So away from the zeros of the square roots, then this differential works. It's homomorphic, and you might think that whenever you're approaching one of the E points, then it's not quite homomorphic. But this chart is technically not defined for those points because it's not, that chart is not homomorphic there. So you move to a different chart, which is the y coordinate. And the y coordinate, you actually substitute, from implicit differentiation, you can get a formula for dy, for dx in terms of dy, and you obtain this representation. And you can see that when x is near one of the e's, as long as the e's are distinct, then the bottom is not going to be equal to 0, and then you can check that this is again homomorphic. So you can, by working on the two different charts, you can actually check this. Maybe a computation that's actually more indicative would be something like the y squared equals x, in which case we have the x, y. In the first case, it's going to be the x square root of x plus or minus, and away from x equals 0, then this is a homomorphic thing. But in the case that, in the other case, near 0, we use implicit differentiation, we have that 2dy is equal to dx 2dy dx over y. So we see that dx over y is equal to just 2dy. And in that case, near x equals 0, we see that this is holomorphic. So it's constant, so it works. So this is the differential that we're going to be working with for the torus. And we'll use this differential to define the objects that we're working with for the solution of the KDV. So more remarks on the homomorphic differentials. So we can actually talk about the spaces of homomorphic differentials. So this is the space of homomorphic differentials. And then you alternatively have the space of anti-homomorphic differentials, which are defined to be differentials that satisfy the complex conjugate of the Riemann-Cauchy equations. So the equations that define homomorphicity, you can take the complex conjugate of them, and that's going to give you an anti-homomorphic differential. And it turns out that this direct sum of these two spaces of homomorphic and anti-homomorphic is it's really equal to h1 of x, which is going to be differentials in x, which is isomorphic to the one-dimensional cycles in x. So these are the one-dimensional cycles up to homology, and which were introduced earlier, and these are going to be for a genus G surface, so it's going to be dimension 2G. And really what I'm trying to get to here is that the space of homomorphic differentials is just going to be dimension G vector space. And in particular for the torus, we're just going to have a vector space that's going to be generated by dx over y. So any other homomorphic differential on the torus is going to be a constant multiple of dx over y. Yeah.
So I always thought of this. So is that this is like the Hodgkin decomposition, right? So I always thought it was the holomorphic plus anti-holomorphic is the like space of harmonic differentials, but is that like, I guess, is there a isomorphism then from that to the H1x?
So holomorphic, from what I remember, is equivalent to harmonic. And then
Full space would give. Right, I always thought right, the holomorphic plus anti-holomorphic gives you every single harmonic.
I don't remember. So from what I thought, it was holomorphic. I thought holomorphic implied harmonic. I thought homomorphic and harmonic are equivalent objects.
No, because harmonic is holomorphic plus anti-holomorphic.
Tom, do you want to break the
Well,
type?
you have to decide if we started with saying harmonics, which means real or complex harmonics. Okay. B. One version of the Hodge theorem is indeed that the real homology, each class of real homology is uniquely represented by a harmonic form, although it's a class of by a harmonic form. And then what we know is that the homomorphic differentials are such that they are real and imaginary parts, or each a real harmonic form. And that's what you're thinking about when you're saying this. So there is a setting where you talk about complex harmonics that almost certainly really mean real harmonics, so that I repeat, you have a harmonic differential, then you can consider just its real part. Right? So what's happening is you've got a harmonic differential to be holomorphic, let me do this. A holomorphic differential, you start evaluating on tangent vectors, you get real and complex, and you get complex numbers, you can just take the real part. That defines, you check an actual real differential. But now you check using the Laplacian, that real differential is in fact harmonic. And then there's the star operator, we mentioned, you're talking about these sorts of things. And that tosses the real part of a holomorphic differential to assign its imaginary part. So there's a natural pairing of the real harmonic forms that get you to the holomorphic. That's the beginning of the story.
Yeah, so then is there some morphism implied here that has to be explored for X, I guess. Okay.
Yes, the short answer is yes.
Okay, and do you know where I could read?
Yes.
Is that like an L order?
Yeah, I would look at Parkinson problem. They do a very nice representation of this. In particular, they do some of the Hilbert space theory of really the finer points of this, which it looks to me like comes up deep into the Kdv. For me, yes, Parkinson problem.
That's it. I read that before, so I'll get a copy. So.
I'm gonna attempt to.
It's freely available from the Oregon State University library.
Farkas and K.
KRA.
Cron. Farkas
Yeah.
and Cron. Okay, that's a great reference. Thanks, Tom. I just yeah, my background is this is not a solid, but so I appreciate the help. I just know the facts.
Sometimes one only wants the facts, right?
Yeah. So, all right. So, so in particular, we just have for g = 1, we only have one holomorphic differential, and this is an object that we'll be working with. For genus G, we'll have G linearly independent holomorphic differentials, and they're easy to construct, and the book gives us a construction. But in this case, everything is simpler since we only have one. So now let me introduce in the able map. So the first observation is that the integrals for the Riemann surface are going to be path independent up to cycles. And here I have a representation where I have where I'm taking 2 points in my Riemann surface. I think a lot about the points in the base, and then I kind of lift up to the surface. But in particular, I take 2 different paths. Path gamma 1 and gamma 2 from P0 to P1, and then I consider the integral along these 2 different paths, and I have that the integral of omega along phi2 is going to be equal to the integral along phi1 plus this cycle, plus the integral along this cycle. So in here you can see that if I want to do the integral to P1, I can follow P2, and then I can come back and then go back this way. So this first part over here is going to be equivalent to my cycle of gamma B, and then I'm going to have the second part is going to be this. And this is going to be the typical way that you deform contours as in complex analysis, because you can locally do it in the charts. You can deform contours, except that you cannot go over, you cannot cross the ramification points, the branching points. So in here, what I'm gonna do is I'm gonna normalize this homomorphic differential. I'll call it, since we only have one, I'm just gonna call it omega whole, which is going to be I'm gonna multiply it by a constant c, such that when I take the the integral along the cycle gamma A, I'm going to get 2 pi I. And if I take the integral over gamma B, then I'm going to get some B, which is just defined this way. And the able map is going to be a map from my Riemann surface to the Jacobian, which in this case, wait, is it Jacobian variety or Jacobian? What's it called? Jacobian? Because
Get to have your choice, sure, right.
Jacobian variety, because I just called something a Jacobian, which is a transformation between coordinates. Yeah.
These guys do too much work about it.
They have no life, I guess. So A, this is a script A for Abel, and it's going to be a map. So in here, it's going to be mapping point P via this integral from P naught to P, where we don't specify the path anymore because it's up to cycles, which are given here. So if the difference of two numbers in here is up to a linear combination of the cycles, then it's considered the same because we're doing it modulo this. So we define map here A from the Riemann surface to this Jacobian variety, which is just the complex numbers modulo the cycles. And in here, I wanted to take a second to actually show that this constant actually exists, because essentially what I'm doing is I'm defining C. C is defined to be 2 pi I over the integral omega A, or the integral of omega over gamma A. So this is the way that C is being defined essentially. And for this C to be defined, we actually have to make sure that this integral in the bottom is not equal to 0. Otherwise, we can't define that normalization. So I'm introducing the Riemann bilinear relations. So I'm going to take my typical omega, which is dx over y. I'm going to define the periods, A prime and B prime. So these are going to be the integrals over the cycles gamma A and gamma B. And to make, and then I'm going to keep integrating over omega. But to make the integrals well defined, I'm going to take my Riemann surface and I'm going to cut it out into a rectangle. So I'm going to cut along gamma B and I'm going to cut along gamma A. And now I'm going to define an interval gamma, capital gamma of P, which is going to be, I'm going to fix a base point P naught, and it's going to be the integral of omega along this path. And since I've cut out my Riemann surface, this path is unique, and I don't have any issues of being defined up to the cycle. So this is a well-defined function on what I call the interior of X. So in here, I just have one specific choice of path and up to deformations. And one remark is that the differential of omega is lowercase omega. And this is just by the fundamental theorem of calculus, really. And so we have this. And then I consider this integral. This is going to be the complex conjugate of my function that I defined above, of my integral, times d omega and integrated along the boundary of the interior. So it's going to be integrated along this path near the boundary. And here I can use Stokes' theorem, and actually write this out as this following differential along the inside of the interior of the Riemann surface. And we have that this d omega and this d omega, it's going to be omega bar times omega, and integrate over the interior. And we have that this is the complex conjugate. And again, we have a specific form for omega. which is going to be dx over y and dx over y. And since we're taking the complex conjugate, we're taking the complex conjugate of each of the coordinates. And in particular, I'm going to write x into its real and imaginary part so that I have that dx is going to be dxr plus I dxi, and dx bar is going to be dxr minus I dxi. So this is the complex conjugation. And when I take the wedge of dx and dx bar, I have that this is equal to 2I dxr dxi. I'm assuming that you're familiar with the wedge notation. Is that okay? Because that's where the magic happens. So summing up this, I have that this integral is going to be this dxr dxy, which is really a volume form, local or a infinitesimal area. And then this times this is going to be the absolute value of the norm squared of y. So this is going to be a positive quantity. And that means that this is going to be, and we obtain this 2i from here. So it's going to be 2i times a certain area of the interior. So it's going to be a positive quantity, this area. And so we evaluated this integral one way using Stokes' theorem. Alternatively, we can just do the line integrals. So in here, we have the same integral, and we can, again, we're integrating this way. And we can write it into 4 components: gamma A minus, gamma A plus, gamma B plus, and gamma B minus. And then I'm going to note that when I pair these 2 components up, I'm going to write it this way. And then in here, I recall my definition of gamma bar, which is going to be an integral from P naught to P. So in here, this gamma bar is going to be an integral from P naught to P here. And in here, I can find for gamma A plus, I can find a conjugate P plus P or P dagger. That's just the same point that when you identify the 2 sides. And what I'm going to have here is that then the integral from P naught to P dagger is going to be this integral. So I can combine these 2 integrals. This one goes from P naught to P, and this one goes to P naught to P dagger to be actually an integral from P dagger to P of omega bar. And that means that I can forget about the base point, and I'm just doing this integral. So it's really just the integral over gamma B. So this is going to be, this is the integral gamma B omega bar, which is just gamma B. We can, complex conjugation is linear. And by definition, the integral over gamma B of omega is just equal to B. So this is just going to be a constant. And then it's going to be B bar. I think the orientation is what gives me a negative. And of this integral here gives me a negative. And then I'm just going to have, I pull out the constant and I have A minus D omega. And by definition, that's A. So this is going to be minus B bar A. And so that's how we evaluate, we pair up these 2 terms, and we can evaluate this integral, this 2 integrals to be minus BA, B bar A. And then we pair up the other 2 integrals the same way. So it's the same idea. And when you go through it, you get A bar B. So what we obtain here is that this integral of this line integral over the boundary of the interior is going to be minus A B bar plus A bar B, or which is equal to 2I, the area of X naught. And in particular, this is going to mean that if the area is not equal to 0, then that means that A is not equal to 0. So since we know that this is a positive quantity, if A were 0, then this would be 0 and this would be 0. So we know that A is not 0. So we know that the integral over gamma A of omega, which is defined to be A, is not equal to 0. So we can normalize. And additionally, once we normalize, we can assume that A is going to be 2 pi I. And once we have 2 pi I, we can again put it into this formula. And if we put 2 pi I into that formula, we have this computation. I put in here, and then I see that the real part of B is going to be minus the area over 2 pi. So I see that the real part of B is going to be negative. So these are two properties that we have about the periods from this Riemann bilinear relations. And this relation is generalized to higher genus, and there are more, but these are the ones that we need right now. The other ones that generalize are that AB, in a certain way, there's going to be a relation that generalizes that says that AB minus AB is equal to 0. For genus 1, it's just trivial, but for higher genus, it's not going to be trivial. Let's see. Oh, yeah, I just have these 2 slides. How are we doing on time? 3 minutes. All right, I'll finish. So I'm going to introduce differentials of the second kind. So in here, this is going to be a differential of the second kind. Is going to be omega. It's going to be a differential that it's meromorphic, so it may have poles, but the residue at the poles is going to be 0. So if we actually write this in local coordinates, that means that it's going to be this is BC. DZ. That we can have a Taylor expansion of this differential whose coefficient for the C to the -1 term. If we have this term, then C1 is equal, C1 is going to be equal to 0. So meaning that, again, if you do the Cauchy's formula, then if you compute the residue, then it's going to be 0. And we're going to define, in particular, if we integrate this differential to get capital omega, it means that we have a function whose expansion is meromorphic function that is a meromorphic function, a typical meromorphic function. It doesn't have any essential singularities. So you can just specify, once you specify this part, which is called the principal part, then the rest of the differential is holomorphic. And as we've seen, this space of holomorphic functions is going to be G-dimensional. For our case, there's only one. So in this case, once this is specified, then this is then specified up to a constant multiple. So we're going to come back and finish the definitions of the elements in the solution for the Kdv. So we're going to fix a point P infinity in the Riemann surface. We're going to introduce 2 abelian integrals of the second kind, which are integrals of the abelian differentials, so that the expansion near a local coordinate of P infinity, where C of P infinity is 0, is going to be given by Z to the minus I. So it's going to have a pole omega I. This function is going to have a pole of order -I for 1 and 3. What's that?
Should I be 2 and 3? Don't you want to have no residue?
Oh, this is the integral.
Oh, thank you.
Yeah, this is the integral. Yeah. Yep. No problem.
Integrals.
Yeah. Yeah, the Bilinear integrals. And and then we're going to find this omegas, so that then the differentials would be this d omega 1 and d omega 3, and we define u and capital W to be the integrals around the cycles gamma b of this differentials, and we define d, capital D, to be an integral from p infinity to p of the homomorphic differential minus pi I plus 1/2 of b, where again b is going to be the period of the homomorphic differential and has real part that's negative. And then we arrive at our solution for the Kdv equation with the theta function, and this are the objects that are defined. This is just any constant c, and that's pretty much, now we have a definition of the terms. And one thing that I want to point out here is that the Kdv, the structure of the Kdv actually comes in through this abelian integrals. So by choosing the type of singularity that you have at p infinity, this is what's going to fix your Kdv partial differential equation. Because you can prescribe the singularity to be of any type of polynomial, not just like this simple polynomial of order ci. It could be a linear combination of different powers and stuff like this. But if you change them, that's going to change your differential, your PDE. But if we make this choice, it's going to give us the Kdv equation. So this is where the Kdv equation is hiding, by taking this choice. And so that's it. It took a while to define the objects. We have somewhat of a grasp on them. And the next meeting, I want to give an argument of why this is a solution. Because even though we've now defined all the objects and we can potentially write everything explicitly, if we try to plug this in to the Kdv equation and try to check it, then by hand, we're not going to be able to do it. We're going to have to do a way around it to actually check that it's a Kdv equation. And it's through a different characterization of functions defined on a Riemann surface. So we're going to have to go back to the theory of Riemann surface to actually check that this is a solution, because I don't think it can be done by hand.
Well, you also know this is, you can't, well, it's equivalent though to the traveling wave.
Oh, for this one?
Yeah.
Uh,
I think there might just be some like tricks you can do to do it by hand, because
for genus 1 or for general genus?
genus 1.
Okay. For genus, yeah, I believe, yeah, but I believe that it's still, I believe that you can do it, but you still need tricks. You can't just like take derivatives and then check that all the things cancel out. You probably need extra identities to have the cancellations. So
Yeah,
if you don't have identities, you need some sort of machinery to like check that there's cancellations. There's non-trivial cancellations.
Yeah, definitely.
So I guess that's what I wanted to say. And one way to check these non-trivial cancellations is using the theory of Riemann surfaces. And there are other methods.
Well, I just wanted to mention this for like Alex, and your Alex has seen traveling waves a lot, so that's the main reason.
Great, thank you.
Also, I think the U and W are related to the nonlinear. Like, you get that like nonlinear spur. Those two.
Yeah, I'm less familiar with that.
Yeah, I think that's kind of the way that.
Also, let's give you the solution.
Yeah.
And then do the well, I mean, in also focus more on data analysis. So how do you, if you're given the time series and you assume stationarity, periodicity, and all that, then how do you identify all your U's, W's, and D's and their matrices? So if you have a time series, you want 1,000 components, then you have 1,000 by 1,000 matrix.
Wow.
Yeah. And then the computation becomes very hairy because some of them, you know, your branch points are very close to each other. How do you differentiate them?
Yeah.
Yeah, and then when you're, you know, when you are pointing on solid form, then the solution of the elliptic equation have an m, and the m is like 9.99999 to 20 something figures, and the machine is very difficult to identify when you have a whole bunch of solid ones that you differentiate. So this is a very good background. I learned a lot just by this because I can't read the book because of this, but now I think I understand.
Oh, yeah, thanks a lot for doing this, Axel. It's really good. Actually, are you gonna post those slides?
Yeah, I can post the slides.
So where do I find the video?
The video, I'll send it to Pat. I'm recording right now.
We can
And
put all the videos in one place. The last two, last lecture was very helpful.
thank you. Yeah, I'm also just going through the book and trying to like grasp whether we can create examples. And luckily, I know the facts. I don't know the proofs, but I know the facts. So yeah, I'm happy that this is helping. And
Also, this perspective, like as soon as you go to Kdv equation and you don't have hyperliptic curves, you need to understand everything in this example. I just don't have yeah, so yeah, very, very
yeah, thank you. Yeah, and so next week I'll try to give the proof or sketch the proof of why this is the solution of the Kdv. All right, let's call it.
So will you cover Kdv equation as well?
I think maybe, I don't know if I'll get to it next week, but potentially the week after that, I can generalize everything to general genus. And I guess I can cover the KP for genus 1 maybe next week.
Okay.
Right away.
Well, no worry. I think
Yeah.
I'll be very happy if you spend the entire form. Yes. Yeah. So this applying to the